unable to change it for some reason.
Oh, it's no problem. Yeah. We know Pamela very well. Okay, so I think we can begin. I was commenting just a bit earlier before you joined, Dr. Santilli, that and Dr. Georgiev, that I think we should sort of review sort of where we are at in terms of this particular series of lectures and sort of how many, well, approximately how many more lectures would remain for Dr. Georgiev to sort of complete the cycle that he has in mind. Dr. Georgiev?
Yes, maybe to the end of June, because I have prepared all geometry, and there are too many lectures. I think that if we work every week to the end of June, we will have lectures, no problem. Last week I have unexpected travel, and this was the reason for which I moved my lecture for today. But so many lectures because now we study Iso-Analytic geometry. After this, Iso-Differential geometry. And there are...
Yes, and I think as you proceed, this becomes more relevant to the physics, perhaps. And,
yes.
Also, I should comment that Dr. Sobchak is, and to some extent, Dr. Santilli are sort of continuing some draft work, especially on geometric algebra. And I think we should plan on devoting at least some lectures, maybe intermittently, depending, say, on your own plans. We might decide to include a lecture on that work as well.
So
I'm not sure.
I propose 1 week lecture by 1 week lecture in geometric algebra and 1 week Iso-Analytic geometry. Next week to be geometric algebra, then next week to be geometry, and in this way 1 week algebra, 1 week geometry, and to have lectures every week.
Yes, I think we can adjust it as necessary in terms of comments and progress in each subject. And Dr. Cruz, I mean, did you have anything in particular in mind in terms of subject matter that you were sort of hoping to address or to bring up?
I was working with the idea of following the formalization of abstract algebra, trying to compare with the definition of ISO numbers, ISO algebras, and then I have been working in that. I have not too much progress, but I am working in this, and maybe in a few weeks I can present some of these ideas.
As I recall from your discussion last week that you expressed the view that the isopity should be considered in terms of an algebraic map. Is that?
Yes, yes. This is the principal idea, and then to explore what kind of maps are we using in these formalism.
At the more abstract level, then.
Yes, yes, yes. Mm-hmm.
Okay, I think that's a very valuable contribution to this work, because I still, at least personally, have some struggle with understanding the role of isopity, especially its physical interpretation. And I know Dr. Santilli takes a very coordinate-based, sort of representation-based view of the application, but that is a little bit counter to, or it is sort of counter to the view that physics should be expressed in a more abstract way, or like the goal is sort of to achieve a more abstract expression in physics as a way to, as a goal for the application of mathematics to physics, I guess. And I was just going to comment that this view of considering isopity in terms of an algebraic map counters that view, counters saying that isopity is not necessarily related to a particular coordinate representation. And so I think,
yes.
And Dr. Santilli, you wanted to comment?
Allow me to, I think your difficulties are very understandable, but however, we should be objective in appraising our series. It is my personal view, again, I hope to be wrong, but it is my personal view that those difficulties that you have will remain forever until you remain at the pure mathematical level. Because ultimately our intuition has to be faced with reality. Also, let's not remember that our series of lectures is fundamental problems not in mathematics, fundamental problems in physics. Now, so if you want to answer, at least to attempt an understanding of physical meaning of we should do an actual model. For instance, look at the representation of all characteristics of the neutron in its synthesis from the hydrogen atom and the core star. No, not enough. You have to see first at the non-relativistic level, and then you have to see at the relativistic level. And then you will see that, for instance, the ISO unit alive becoming crucial and fundamental. But this was my 5 minutes presentation on the physical meaning of the ISO unit, which has remained undelivered now for a couple of months. So, my suggestion is that if we remain too much on the abstract level, I see something. Honestly, I see some danger in the value. What we are doing is extremely important, but there has to be a connection with physics, to be honest with you. Otherwise we may lose the contact with reality. But that's entirely
I agree. I agree with your motivation. Like, just to make myself to clarify my point a little bit, is that I agree that we need to be focused on physics when we think of the application. But I do have this tendency to think that intuition gets in the way as much as it. So the insisting too much on intuition tends to limit the type of thinking one can apply in relating mathematics to physics. So I'm not sure if I can make that so clear, but so I object, for example, to think of gravity in terms of geometric terms. So this is a really thing that bothers me, is when people insist that general relativity is about the application of geometry to gravity. And I think that this is clearly not the case, right? That gravity is something physical that we can measure, and that insisting on representing it in one way is missing fundamentally some aspect of the physics.
Yes.
And so by trying to lift the subject, and this is where I agree with you, Dr. Santilli, that's important to lift the concepts to a more abstract level. And so that you relate physics to the abstract mathematics without being overly focused on the representation as such.
I think you should try to keep sight of geometry. I really do think geometry is fundamental to the ideas.
Yes.
Well, as you know, Einstein, they think it's gravity curves space. Well, that's very geometrical. So trying to understand.
Yeah, well, I think it is very geometrical, but it's wrong, right? That's the problem, right? That space is not something that can be curved. Space is something that we can choose to treat as curved if we want to use that particular mathematical representation. But to give space a physical reality, like to make space a part of the ontology is premature move, especially because even Einstein, for example, showed in the 1930s that gravity could just as well be described by torsion as it could by curvature. And these are two different aspects of differential geometry, two very different aspects of differential geometry. And so we might as well say that, say, gravity causes the twisting of a space as well, you know, and I think both pictures are not where you want the discussion to be. You want the discussion to be at a higher level without worrying about the representation. So, I don't know. Dr. Santilli?
If I may, I could not agree with you more, Dr. Page. Let's go back a century back in time. And these are the first historical objection against the conception, against the reduction of gravitation, which is a physical force, to curvature. Space was conceived then, it is conceived now, could be totally empty. There is no structure whatsoever, otherwise we violate special relativity. So the idea that a space which is totally empty, whether curved or not, could could motivate the trajectory of an enormous planet as Jupiter, is not plausible. It's just so you're talking about a pure mathematical conception. I do not believe that space the curvature of space can actually be the propelling force for the planet. No, I'm sorry, I don't believe it. But that is connected to the many other problems in the gravitation, such as the lack of a first order source in the right hand side of the field equation, which will essentially remove the conception of reduction of gravity to curvature, many other problems. I think gravitation is one of the most controversial theory of the second century. It will last for a long time. No change. It will remain like this for a long time. But I never accepted this description as final. You know, it's a majestic conception, geometrically beautiful. It is historical, and you can make a long list of magnificent discoveries. That's why Einstein is Einstein. But the conception of them, but there's been now 1 full century frozen on those basic ideas, and the fantastic papers that I've seen myself as a reviewer have been trashed out essentially for politics. But according to the majority, according to so-called academia, orthodox academia, the gravitation is supposed to remain like this until the end of time.
I like it too much the approach of Professor Osioi about mathematics and physics. He thinks about that mathematics is first. He used to say mathematics is first, and then this is one instrument that can that permit to us to express the reality around us. And then using mathematics, we are building that interpretation of reality that we say that is the physical world. Then in this way, mathematics is extremely important, because if we have a good language, then we can describe the natural world in a correct way. In this way, ISO numbers, ISO mathematics is interesting because maybe, I don't know, I'm not sure yet, but maybe is presenting to us a different view, instruments for express the reality. And then we can find another properties in, with this mathematics. Then this is my idea when I want to explore in the more abstract level what is isomathematics. I don't understand yet if it is different of the mathematics that we used to use, or this is only one subset of that.
So, firstly, I would like to mention that isomathematics is based on the classical mathematics, but yeah, isomathematics has some specific rules for multiplication, division, and then for other terms in algebra as determinant of matrix, what is the isomatrix, iso-inverse, and so on. Then we can consider this as a new subset of the classical mathematics, because Professor Santilli firstly observed that if we take some object from mathematics and define in a new way multiplication, division, and then differentiation, we obtain new classes of objects with specific rules. These new classes of these objects with these specific rules is called isomathematics.
Yes, I understand your viewpoint, but if when we say that we use different rules for multiplication, addition, etc., we are thinking in one kind of this operation. But if we define this operation in the most abstract level, then there is no difference because the rules are the same.
Yes, it's just a matter of representation. Right?
Yes.
With
yes.
the most important point. You see, again, you raise a very important question that must be discussed, and I'm so grateful that you asked this question. But again, it is my personal view that cannot be answered without a physical input, at least partially, not entirely, because that's a bit. Because if you ask me, what is the mathematics of what is the meaning in the representation of nature? The mathematics is supposed to represent nature. So what is the meaning, the most important meaning of the mathematics of the 20th century? I have a very direct answer. Is the mathematics the best possible mathematics for the representation of interaction derivable from a potential. The algebra are Hamiltonian, and Hamiltonian can only represent potential interaction. Once you see this, but then you have the question is, what is isomathematics? The answer is one and only one with no ambiguity. It's the only known mathematics, as far as I know, that describes the interactions not only derivable from a potential, but also non-derivable from a potential, which are the most important interaction in the nuclear structure. In other words, until you remain, when you talk about mathematics, in my mind means atomic structure, interaction that are derivable from a potential. Isomathematics, you have to think about nuclear structure in which the interaction cannot be only derivable from a potential, otherwise nuclear should explode because protons are positively charged and they repel each other with a monstrous force. The only force that can counterbalance this repulsion are the contact interactions, zero range. They are not derivable from a potential. They are originated in Newton's equation, the Lagrange or historical equation with external terms, etc., etc. The isomathematics, the only way they're capable to represent them, so that Dr. Georgiev pointed a very, very nice point. Dr. Georgiev, thank you very much for pointing out the existence of very precise rule that you mentioned, Dr. Georgiev, are the very precise rule that allow physicists to add a non-contact interaction in the nuclear structure, in strong interaction at large. So, but the beauty is that by preserving the axiom of conventional mathematics, because we cannot abandon the axiom of special relativity. It's a beautiful axiom. We cannot abandon the axiom of quantum mechanics unless there is a serious problem. No, what isomathematics has indicated is that no, we can preserve the axiom of quantum mechanics, but realize in a more general way, as very precisely described by Dr. Georgiev, and add those contact interactions. Remember, proton and neutrons are one inside the other in a nuclear structure. Those are contact interactions. They cannot be derived from a potential. They are technically, they are variationally non-self-adjoint. So this is basically, if you add physics, then you have no ambiguity, none are completely excluded. And you see clearly the differentiation, external problems, namely problems, that's also for gravitation, external problem, namely point particle in vacuum. That's what we know is beautiful. There's nothing to add, zero. And then, but we have all interior problems in which they need extended representation of extended character and all possible interaction, not necessarily those derived from a potential. This is okay. 2 centuries ago, already a century ago, became questionable. But so that's so from a physics, if you add some physics, there is no ambiguity in the answer. Indeed, you go to the Newton force. The Newton force is divided into potential and non-potential. Newton was the first to conceive velocity-dependent forces that are not derived from a potential, and their variation are non-self-adjoint, not derived from a potential. And you do all the process that Dr. Georgiev indicated step by step, and you arrive with that the Newton force is very precisely represented by, not by the iso unit, carefully, by the isotopic element. And the iso unit represents the inverse of this non-potential interaction. This is the part which we never saw, and maybe one day we'll see it.
But I think that one way of reconciling your two views, like Dr. Guzman and Dr. Santilli, would be to focus on what you said about preserving the axioms. So isomathematics preserves the axioms. So it's in that sense that at the abstract level, isomathematics doesn't really add anything.
No,
except that what it does insist on, what it does demonstrate, is that something like non-contact, contact interactions are actually built in already at the abstract level.
Yes.
So that when we express physics abstractly, we're already doing the right thing, right? If we insist that physics depends on a particular representation, then we've gone down the wrong path, because isomathematics is a representation of those same axioms, right? And so it's not so much that we should choose so much a traditional conventional representation or an isomathematics representation, but rather, to the extent possible, raise physics to the abstract level, right? So, and isomathematics is valuable in that regard because it forces you to realize that at the abstract level, physics already has what's required. It just hasn't been built to emphasize that particular aspect of those axioms. Now let me add one more point that I'd like to try to bring in Dr. Sobczak, because although some of my comments suggest maybe that geometric intuition is not a valuable thing.
It seems to me like you want to erase geometry. I don't think that's really.
No. See, that's where I want. That's the impression I want to correct. What I'm hopeful about, especially in the work that you're doing on isogeometric algebra, is a demonstration that there are more powerful representations which incorporate both conventional geometry and isogeometry into one more, how should I say, more richer, a richer environment. So geometric algebra provides a very rich algebra to express geometric ideas. And within this richer structure, one can actually see the relationship between non-isomathematics and isomathematics actually played out within the structure. So instead of thinking of moving from one structure to another, we can see in this richer structure how these two relate. Like that's the kind of hope that I have. And maybe it's for that reason that Dr. Sobczak, you have been sort of insisting over many years that geometric algebra needs to be applied more widely in physics, right? Because it's because it's richer, right? And so it's a wider set of representations, which hopefully you can actually demonstrate include a lot of the types of representations that Dr. Santilli has been saying is missing from physics. So by insisting that physics take a more geometric algebra view, you're actually bringing along at least some of those aspects that Dr. Santilli is looking for.
Yeah, I'm really going so far as to say that a matrix is just a coordinate representation of a geometric number, which consists of multivectors, vectors, bivectors, trivectors, in any number of dimensions and with any metric signature. So, but any matrix can always be interpreted as a matrix of a geometric number. And of course, that's where the geometry comes in. You can ignore the geometry, but I think the geometry is always underlying the abstraction, really. If you're with linear algebra, it really has a geometric interpretation, or many geometric interpretations, some which are important, maybe some in which you're saying are not important. That is possible. So anyway, it's a discussion to continue.
But this view of geometry, can, like say, classical geometry versus geometric algebra, I think geometric algebra has tended to keep the classical picture a bit, right? And so for that reason, we don't see operations in geometric algebra that say mix vectors and bivectors except in very specific ways. Like so we produce things like paravectors as a
electromagnetic field mixes a vector with a bivector, namely the electric field and magnetic field.
Yes, no, but that's what I think that's how should I say this? That the isogeometric algebra has this mixing built in to the it sort of adds formal structure to geometric algebra to provide that sort of mixing in a natural way. Like,
okay, that's interesting. How do you represent electromagnetic field in terms of an iso-geometric or an iso-algebra? How is it? Is an electromagnetic field changed when you go to an iso-algebra? Perhaps Dr. Santilli can answer that.
Yeah, well, but you have to clarify the question. Electromagnetic for electromagnetic field in empty space, in vacuum, iso mathematics absolutely inapplicable. Not only inapplicable, if you try to apply, you end up with physically experimentally verified. So you have to think the geometry. That's one of the reasons, Dr. Sobchik, I'm so in favor of your work on geometry. You have to think of an electromagnetic field, but light propagating within an inhomogeneous and anisotropic media, such as our atmosphere. Then you have the question, how do I describe that? Well, the only way that I know how to describe inhomogeneity and anisotropy, you need geometry. Without geometry, you cannot do that. But then you see that matter alters the geometry, that not of space, empty space, or the ether, the universal substratum remain always the same. We're talking about the geometry of our world, the way we represent our world. But then you see so in the electromagnetic waves in empty space, and the Minkowski line element is absolutely perfect. There is nothing, but it's experimentally verified so many times to begin with. But then you go to the electromagnetic waves within our Earth, then the only representation that has been experimentally verified is the Iso-Minkowski representation since 1983, which has been now a number of experimental verifications. It implies electromagnetic waves that can absorb energy from plasma, waves that can really lose energy to a cold medium. That is the experimental verification of the Zwicky hypothesis of tire light as the origin of the expansion of the cosmological redshift. And then you see a number of physical applications. But so far we have seen no experiment that has disproved the isomathematical representation of electromagnetic waves within the physical medium. I have many papers I can send it to you if you are interested.
Yeah, okay. I think we should allow Dr. Georgiev to continue with his lecture.
Okay.
I'm sorry that, but I do think sometimes we need to take a break from the mathematics and focus a bit more on physics. And so I hope you bear with us, Dr. Georgiev.
Okay, thank you. So today we'll consider what is the iso angle between two isovectors, isoslope of an isoline, and then we'll define isocircle and we'll investigate the basic properties of the isocircle. So suppose that head V and head W are two isovectors. Iso angle between the isovectors head V and head W is defined as follows. In this way, also for an iso angle, we will use the following notation. Here in the definition of the iso angle between two isovectors participate the iso inner product of both isovectors. Also, the iso length of every one of the isovectors. And in the end, we take the iso inverse isotrigonometric function, arcus cosinus. In fact, if, yes?
Ask one quick question. Yes, here where you have the, this subscript here, do you see my annotation?
Yes, so
could
because
you explain that?
Yes. See, we take a vector, isovector, in which the first coordinate depends on the isotopic element hat T1. The second coordinate depends on the second isotopic element. In the previous lectures, we saw how to add and subtract two isovectors using addition and subtraction by isocoordinates. But when we operate with iso numbers in different isofields, when I say that we operate with iso numbers in different isofields, I have in mind that in one isofield we have as basic isotopic element hat T1, and in the other isofield we have the basic isotopic element hat T2. But when we take a combination between elements from different isofields, we define the basic operation iso addition and iso subtraction, iso division, and so on, using the other basic isotopic element, which is denoted by hat T. When we have iso inner product, the result, because we have iso coordinates, then the result is an element of the isofield, which depends on this isotopic element hat T.
Dr. Georgiev, I would like to make a comment, if I may. We had a discussion, I believe, that even before you came, but regarding the two alternatives of using your approach of using isotopic element per each individual coordinate, or the way we do it in physics with one single isotopic element, which will be the n dimension. However, I made a number of times the point that your approach, namely to have individual isotopic element for each variable, it may well results to be mathematically more appropriate and more accurate than what we use twice. So this is, I believe this is precisely a case. Here we have a case in which we have, of course, an isotopy for the space, but we have also an isotopy on the angle. And then you need an isotopic element for the angle, which has to be independent from the isotopy for the coordinates. I do honestly, if you ask me the question, if I can do all this with one single isotopy, my answer is I do not know. And so I would like to elaborate. This was my point with all colleagues about this beautiful series. This was an illustration of my point that Dr. Georgiev, your approach has to be mathematically more correct than what we use in physics.
I guess my comment was sort of motivated by wondering why you don't just simply define arc cos as an iso function of some sort, like so why the notation doesn't just show a hat over the arc cos, whereas you've written subscript T.
Yes, if we define as iso function, we will get the same result. But now, because we have started from what is this iso number, iso matrix, iso determinant, and so on, we have not yet introduced what is iso function. After we move to iso-differential geometry, then we will use the notation for iso function. Because now we suppose that all participants are not familiar what is this iso function. Now we have defined iso number, operation with iso numbers, and what is iso trigonometric functions. After we learn all iso-analytic geometry, then we will move using the iso function to solve current iso-differential geometry. But if we use the approach as it is given in the books, Foundations of Iso-Differential Calculus, and use the definition for iso functions, then we will get the same result.
Okay.
There are, there is not any differences between this definition and if we use a definition using iso function.
Yes.
Okay.
Okay, that's clear. Thank you.
Okay. So in fact, if we use the definition for iso inner product, iso length of an iso vector, we will get the following representation of the iso angle het alpha. In other words, the iso angle het alpha is equal to this quantity. Here participate the basic isotopic element het T. Here participates the basic isotopic elements het T1 and het T2 in this way. If these isotopic elements are equal, then we get the case in which here we will participate only one times the isotopic element. If these isotopic elements are equal to 1, then we get the classical case. And from here, we will use the following representation in the direct representation of the angle and iso angle. So as first example, we'll consider if the isotopic element het T is equal to 2, het T1 is equal to 3, het T2 is equal to 4. We take two vectors, V and W. Their isolifts is written as het V and het W. And these isolifts are written in this way. So the iso inner product between the both iso vectors is equal to 3. Then we compute the iso length of the iso vector V, and its iso length is equal to this quantity. Then we compute the iso length of the iso vector het W, and it is equal to this one. And from here, using the representation of iso angle, we get that the iso angle between these both iso vectors is equal to this arcus cosinus. And the corresponding isolift is equal to this one. Observe that the angle, classical angle, between the classical vectors V and W is equal to this angle. But the iso angle is this one. There is big difference between the iso angle and the classical angle. These two quantities are very different. As next, yes?
Allow me to indicate or illustrate to our colleagues the enormous physical implications. And this is in regards to the scattering theory. Now there are billions of dollars that are spent, Fermilab and CERN, etc., on high energy scattering. What are they? Well, they send the proton against a target, a hyperdense target, and then there are all sorts of particles that are produced. All calculations are based, including the physical conclusions of prediction of new particle and characteristics of new particle, are based on the theory, on the hypothesis, extremely debatable hypothesis that the notion of angle, as it appears, classical, as Dr. Georgiev describes classical, the same notion of angle in empty space also applies inside the scattering region. Absolutely, this theoretical assumption has been attacked, should know has been attacked repeatedly, because physicists, both the national and the international physics laboratory, now they continue to use a mathematics that is simply inapplicable in the interior and hyperdense medium as it is a target. And I just want to mention to you that once now there is no scientific process in the use of public funds at the national lab. If one day, maybe next generation, there will be a scientific process, all experimental results from, mark my statement, all This has been discussed by technician experts in scattering theory at our conference, the 2020 conference. All claims of experimental results by Fermilab, DAISY, or CERN have to be numerically revised. And the mathematical origin is here. The physical origin is that when you have mathematical origin is beautifully described by Dr. Georgiev. The physical origin is that when you send the proton in a collision in a hyperdense scattering region, you cannot ignore the contact interaction. So the contact non-potential interaction, they manifest themselves with deviation from the very conception of an angle, and of course with experimental verification. Sorry for the deviation, Dr. Georgiev, but I thought our colleagues should know the enormous implication of what appears to be a very simple formula.
Yes, thank you. So as next example, we consider when the basic isotopic element hat T is equal to 2, hat T1 is equal to 1/3, and hat T2 is equal to 4. We take two real vectors V and W. Their isolifts are given in this way as hat V and hat W. Then we compute their iso inner product. In our case, is equal to -23/4. After this, we compute the iso length of the isovector hat V and the iso length of the isovector hat W. And after this, we're ready to compute the corresponding iso angle, which is equal to this number. Again, after we use the classical rules for the classical angle between the classical vectors V and W, we get this angle. Again, we see big differences between the iso angle and angle. As the first example, we consider the case when the isotopic element is equal to 1/2, the isotopic element hat T1 is equal to 1/3, and the isotopic element hat T2 is equal to 1/4. Take for two classical vectors V and W to be these vectors. Their isolifts, in our case, for these isotopic elements, are these isovectors. From here, again, we compute the iso inner product of the above isovectors, and it is equal to -7. After this, we compute the iso length of the isovector hat V and the iso length of the isovector hat W. And for the iso angle between these isovectors, we get this number. But the classical angle between the classical vectors is equal to this number. Again, both numbers are different. After this, we were ready to define what is isoslope of an isoline. If any two isopoints on an isoline are taken, their join makes an isoconstant isoangle with a fixed isodirection, and the isoangle so formed is independent of the choice of the isopoints on the isoline. This is precisely of saying that any isoline has an isoconstant isoangle, and it is customary to measure the isoangle hat alpha, which an isoline makes with the positive isodirections of the x-axis. The quantity isotangents of alpha is defined to be the isoslope of the isoline. Now we will find a representation of the isoslope of an isoline. For the consider both vectors hat E1 and hat E2. Note that this is the basic iso unit isovectors on our iso-axis. And this
excuse me, one little question. Why do you use in the definition of the vectors isobectors E1 and E2, the exponent of 1/2 in T.
In T, here.
Yes.
This one, because see, we have to get that this iso-vector has iso length, which has to be equal to 1/het T1. And this is the reason after we make the direct computations to get iso length is equal to the 1/isotopic element. Here we have to have power 1/2. Otherwise, the definition will be not correct. Okay?
Okay, thanks.
Suppose that the isoline het L is an isoline with isodirection, isovector het V through the isopoint het P with respect to this isobasis het E1, het E2. Then using the definition for isoangle, we get that the cosinus of the isoangle is equal to this quantity. And the sinus of the isoangle is equal to this quantity. Using the definition for the isotangents, we get that the isoslope of the considered isoline het L is equal to this quantity. From here, the equation of the isoline het L can be written in this way. Note that this equation of the isoline het L is consistent with the other equations which were given in my previous lectures. And this last equation we can rewrite in this way in details. Since this isopoint het P belongs to the isoline het L, we find that P2 over isotopic element of power 1/2 has the following representation. And from here, we find this constant C, which participates in the equation of the isoline het L. And from here, we get the following equation of the isoline, from where we get this equation of the isoline, which is the same equation as it was given in my previous lectures. In this way, I show that using the isoslope, using the new equation of the isoline, written in this way, after we make all computation in details, we get consistence with the previous equations of the isoline, namely, this was one of the previous equation of an isoline. So after this, we're ready to give a definition for an isocircle. An isocircle is the locus of an isopoint which moves such that it remains at a fixed isodistance from a fixed isopoint. The fixed isopoint is called the isocenter of the isocircle, and the fixed isodistance is called the isoradius of the isocircle. And now we will find an exact equation for an isocircle. Suppose that the isocenter of the isocircle is the point het C with these isocoordinates and isoradius given in this way. Take the isopoint het X to be the isopoint that remains at the isodistance het R from the isopoint het C. After using the definition, what is the isodistance between two isopoints, we get the following representation of this isodistance. From here, the equation for an isocircle is given in this way. Isocircle looks very close to what is ellipse in the classical case. So as first example, we consider isotopic element had T to be equal to 5, had T1 to be equal to 4, had T2 to be equal to 9. Then the equation of the isocircle with isocenter, these isopoints, and isoradius had 1 is given in this way. In the following picture, in the red color is given the classical circle, and its isolift is this isocircle. In other words, the isolifts of the isocircles are ellipse in the classical case. As next example, we consider the isotopic element had T to be equal to 7, had T1 to be equal to 2, had T2 to be equal to 3. Then the equation of the isocircle with this isocenter is given in this way. In the next figure, in the red color, is shown the classical circle, and in the blue color is shown its isolift. Isolift is an ellipse in the classical case. And as first example, we consider for isotopic element had T to be equal to 5, had T1 to be equal to 3, had T2 to be equal to 4. Then the equation of the isocircle with isocenter, this isopoint, is given in this way. And in this picture is shown the classical circle in the red color and the isocircle in the blue color. As next example, we show when the isotopic element had T is equal to 2, had T1 is equal to 4, and had T2 is equal to 4. Then the equation of the isocircle is given with this equation. And in the next picture is shown the classical circle in the red color and isocircle in the blue color. So with these 4 examples, we see that in some cases, isocircle is very close to the classical ellipse, but in other cases, isocircle is looks as the classical circle. There is not a rule to say that all isocircles are ellipse. Now we will give an isoparametric representation of the isocircle. Suppose that the isopoint had X has the following coordinates. Then using the rules for isomultiplications and the definition for isotrigonometric functions, cosinus and sinus, we get the following representation for the first isocoordinate of the isopoint had X. And for the second coordinate of the isopoint had X, we get the following representation. From here, using the definition what is isopower, we obtain that the isopower of these 2 isoquantities is equal to R squared. And from here, we get the classical representation of the isocircle. So this representation, which is given with the equations 1, will be called isoparametric representation of the isocircle. In the isoparametric representation of the isocircle, participates the isotopic element had T1 in this way and had T2 in this way. We see that we have difference with the classical parametric representation of the classical circle and the isoparametric parametric representation of the isocircle. As the first example, we consider the isotopic element had T1 to be equal to 4, had T2 to be equal to 5. Then for the isoparametric representation of the isocircle with isocenter, this isopoint, and isoradius head 3, we get these representations. As next example, we consider the isotopic element head T to be equal to 1/2, the isotopic element head T1 to be equal to 8, and the isotopic element head T2 to be equal to 4. Then the isoparametric representation of the isocircle with isocenter, this isopoint, and isoradius head 5 is given in this way. We see this is for the first coordinate, this is for the second coordinate. Now we'll consider behavior of an isopoint and isocircle. So consider an isocircle given with this equation with isocenter, with this isopoint, and isoradius, this isonumber. Consider an arbitrary isopoint head P from our isofield. Then we say that the isopoint head P lies outside of the isocircle head C. We have the following inequality. We say that the isopoint head P lies inside of the isocircle head C. We have this inequality. And we say that the isopoint head P lies on the isocircle head C if we have this equality. And we will consider some examples. If the isotopic element head T is equal to 3, head T1 is equal to 4, head T2 is equal to 5, and if we consider this isocircle, then this isopoint is the isocenter of the considered isocircle, and considered isocircle has as isoradius the isonumber head 2. Then this isopoint lies on the isocircle head C, and it is proved. This isopoint head P lies outside of the isocircle head C, and this isopoint given with these isocoordinates lies inside of the isocircle.
Are there any examples where isocircles are hyperbolas rather than ellipses?
What?
Like...
You need a singularity, however.
Yes, yes. We'll consider and with singularity.
It's positive definiteness, I guess we're talking about then when it becomes.
Yes, they're positively defined and there is no problem.
So there's really no difference between studying circles and ellipses and studying isocircles. It's all contained in studying.
Yes, but as I saw in my first example here, this is the classical circle in the red color. The isolift is this one.
And what's
for
the difference?
this isotopic element. Here is other example where the we have classical circle in red color, and its isolift is this. In this case, is ellipse. Okay. So but we have not strong. Yes, we have not only one rule that the isolift of a circle is ellipse. There are cases in which the isolift in our cases is ellipse, in other cases is circle.
But a circle is an ellipse, right?
What?
A circle is an ellipse.
Yes.
So,
yes.
So this case is included.
Included in the other cases, but when we investigate,
but yes. a lift. I think Dr. Sobczak was proposing that an isocircle is always an ellipse, and it includes the case where this includes the case where an isocircle is still a circle, because a circle is an ellipse, right?
Okay, I agree. but we have to exchange the center of the isocircle and the focus and so on.
There's a different issue, whether the isocircle can also include an hyperbola. The answer is no, under the condition that all isotopic elements are positive, definitely. Because you have a change of topology from a compact to a non-compact topology, the transition from an ellipse to hyperbola. So the answer is no, not under the notion of isotopy, isostopos preservation of the axiom. In other words, you have the infinite family of all infinitely possible ellipses, yes, but you cannot move from an ellipse. You cannot change the topology, and not under the assumption of them.
Yes, so now we will define what is isotangent of an isocircle. Suppose that head P and head Q be any two isopoints of the isocircle head C. The isotangent at head P is the limiting position of the isosecant head P, head Q, through the isopoints head P as head Q tends to the coincide with the isopoint head P. Now we will find an explicit equation of the isotangent of an isocircle. Consider this isocircle head C given with this equation. And we take an arbitrary isopoint head P, which lies on the isocircle head C. Head O is the isocenter of the isocircle head C. Then this isovector head O, head P is the isonormal isovector of the isotangent to the isocircle head C at the isopoint head P. And from here, the equation of the isotangent to the isocircle at the isopoint head P is given with this equation. So, as example, we consider the case when the isotopic element head T is equal to 3, head T1 is equal to 3, head T2 is equal to 7, and consider this isocircle. Take the isopoint head P, which lies on the isocircle head C. Then using our representation for the equation of the isotangent at head P to the isocircle head C is given in this way. So in the next picture is given the isocircle C and its isotangent, but the picture is not very good because here is the isocircle, here is its isotangent. In the classical case, we have classical perpendicularity, but here we see that this is not classical perpendicularity. As next example, we consider the isotopic element head T to be equal to 1 over 4, head T1 to be equal to 2, head T2 to be equal to 3, and the isocircle to be given with this equation. We take this isopoint on the isocircle. The isocenter of the considered isocircle is this isopoint, and the equation of the isotangent to the isocircle head C at the isopoint head P is this one, or we can rewrite in this way. In the next figure is shown, this is the isocircle, this is its isotangent. So
does it end at that point? It doesn't go off in two directions, like going down further? Or why does it begin at that point and then it just ends at the tangent line there?
Yes. Later we will see if we change the point P, head P, to be not on the isocircle, to be outside of the isocircle, then from a point outside of the isocircle, we have again two isotangents. Okay?
A month or so ago, you asked a very legitimate question, namely isotangent. And remember, this is just a friendly comment. And remember my comment Yes, it can be answered, but you need several lectures before the answer can be a technical answer can be provided. So now you see all those lectures are necessary and prerequisite by Dr. Georgiev to provide a technical definition of an isotangent. Sorry for the intrusion, but just a friendly one.
Okay, in this example, we saw that the isotangent is perpendicular as in the classical case. But in the previous example, here, we have not the classical perpendicularity.
I just don't understand why it ends at that point. You don't continue the line further. Even in both, it looks like that isotangent intersects the circle in 2 points then in the other picture. If you continue the line.
Yes. In this picture, we will have 2 points. And in the later, we will see when we investigate the behavior of isoline and isocircle, we have cases when we have 2 intersection isopoints, 1 intersection isopoint, and when we have not any intersection isopoints. But all these cases depends on the choice of the isotopic element. In the, for instance, in the first example, the isotopic elements are these. And in the second example, the isotopic elements are these. Observe that the basic isotopic element is less than 1 here, is 1/4, less than 1. In the previous example is greater than 1. Okay?
No, but still, I think, I don't want to belabor the point, but why not draw the general case here? Like, why do you have it end at the circle?
Because to see where is the point, because when we deduct the equation of the isotangent, we take a point from the isocircle. And then this is the reason for which here they are shown as the endpoint, but this is not the endpoint. Yes, we can continue this. But this is to show where is the given isopoint. It is here. Okay.
But if there are 2 isopoints,
isopoints in the next examples, not here.
But Dr. Sobczak is claiming that in general there are always 2 isopoints. Sometimes they coincide, but
Yes. In the general case, we have 2 isopoints.
So
here
in this
only
case, only one point is a special case. Right?
Yes. This is special case, only 1 point. To see that isotangency in this case is very close to the classical tangency. Look as perpendicular. But in the other case, looks in this way.
Yes, but in both cases, it's still 2 points, right?
Yes.
Really. And so this is a dramatically different notion of tangent, right?
Yes, different.
For example,
different.
It seems to have some trouble with the notion of tangent being a derivative in some sense.
Yes,
and 2 points.
And the definition given here for tangents coincide with the definition of the isoderivative. Later, maybe in May, June, we will see that using the definition of isoderivative, then we can deduct this equation for isotangency.
Dr. Page, you can also think it that the projection,
but now we use other approach, pure geometrically.
The projection of an isotangent in a conventional space absolutely has nothing to do with the conventional tangent. I mean, it's a second in general. So there is the structural difference on the 2 notions.
Yeah, well, it just looks like that last equation, that it can be any line. It's simply that's the equation of just a line, any line that, that you have.
Any line through this isopoint can be.
Or any line that bisects a circle in some sense is a tangent?
Yes. But tangent here we have the basic condition when head P is the limiting position of the isosecant, given in this way, through two iso points on the isocircle head C. And then its equation is given in this way. But we will see that we will have two iso points, and in some special cases, one iso point. Okay. So here is other example. Now we'll give a definition what is isonormal. Consider the isocircle head C with this equation, with isocenter this isopoint, and suppose that the isopoint head P lies on the isocircle head C. An isoline through the isopoint head P that is isoperpendicular to the isotangent at head P to the isocircle head C is called isonormal to the isocircle head C at the isopoint head P. It is very usually to say from now that because we have difference between classical perpendicular and isoperpendicular, here we will have again differences between normal and isonormal. Now we'll give an expression of the isonormal to an isocircle head C at isopoint head P. And this equation can be written in this way. This isovector with this iso coordinates is an isonormal isovector to the isocircle head C. From here, other representation of the equation of the isonormal to an isocircle is given in this way. Here in these equations participates the isotopic element head T1 and head T2. As first example, we will consider our previous examples for the isotangency, and we'll continue these examples to find the corresponding isonormals. So if we consider the first example, for the equation of the isonormal, we get this equation, and here is given the picture. This was the isotangents. This is the isonormal in the brown color. In green color is isotangent. In brown color is isonormal.
Are those isolines perpendicular?
But
isoperpendicular?
Yes, they are isoperpendicular, but not perpendicular in the classical case. And for the next example, we get the following picture. In this picture, we have classical perpendicularity and isoperpendicularity. In the brown color is the isonormal, in the green color is the isotangent. They're both isoperpendicularity and perpendicularity in the classical case. And for the first example, we get this picture. In the brown color is the isonormal, in the green color is the isotangent. For the first case, we have this one. So,
but excuse me, in this one,
this one,
the other one, the last that you put it,
this one,
this one. The isonormal include the center of the isocircle?
No, or no, not in any case, because there are cases in which isonormal does not include the isocenter.
Okay, but then we have problem with the topology here.
with the topology, but topology is defined as iso distance. We have no problem because we can make so-called iso reflection of the corresponding point, and then we will get the isocenter of the isocircle. But isonormal in some cases is connected with the isocenter of the isocircle, but using isoreflection. Okay.
Okay, not clear for me, but okay.
Yeah,
okay.
It's strange.
Strange, yes.
Mm-hmm.
Yes, now we'll consider intersection of an isocircle and an isoline. Again, we consider the basic equation of the isocircle given in this way. Take the isopoint head P on the isocircle, and the isocenter of the isocircle is given with head O. Then we take an arbitrary isoline, and we will investigate when we have this isoline have two joint points with the isocircle, one joint points, and no points in common. And we see that if this quantity is positive, then we have two intersection isopoints. In this quantity participates the isotopic elements in this way. This quantity is very difficult, as we see. And if this quantity is equal to 0, then we have only one intersection with this. Head C and head L have no common points. As first example, we consider, as first example, we consider for the isotopic element head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 2. Consider this classical circle and the classical line. For the classical case, we have two intersection points of the classical circle and classical lines. But if we consider the isolifts, for the isolift of the circle C, we get this isocircle. For the isolift of the line L, we get this isoline. And if we look for common isopoints of isocircle head C and head T, in this case, we get that we have two isopoints of this isocircle head C and isoline head L. The picture is this. In the blue color is the classical circle. In the red color is the classical line. Green color is the isolift of the blue circle. And brown line is the isolift of the classical line, which is given in red color. This example shows that we have cases in which, if in the classical case we have only one intersection point, then in the iso case we have again one intersection isopoints. But this is very private case. We'll consider in the other cases. If we could take for the isotopic element head T to be equal to 2, head T1 to be equal to 1 over 2, head T2 to be equal to 3, and if we consider this classical circle and classical line, then we get that the considered classical circle and classical lines have no common points. For the isolift of the isocircle C, we get this isocircle. For the isolift of the classical line, L, we get this isoline. Now we'll check if the isocircle head C and the isoline head L have common points. And after we do the direct computations, we get that the isocircle head C and isoline head L have no common points. Here is given a picture. In the blue color is the classical circle. In the red color is the classical line. They have no common points. In the green color is the isolift of the classical circle. And in the brown color is the isolift of the classical line. Classical circle and classical line have no common points, and the corresponding isolifts have no common points again. As next example, we consider for the isotopic elements head T to be equal to 1 over 2, head T1 to be equal to 1 over 3, head T2 to be equal to 1 over 4. Consider consider the classical circle C, this equation, and the classical line with, given with this equation. Here we find that this classical circle and classical lines have have as a common point the point P. For their isolifts, we have the following representations for head C and head L. Now we will investigate for common points, and we get that that the isocircle and isoline have no common points. So in this example, we see classical circle and the classical line have one common point, but their isolifts have no common points. This is the picture. In blue color is given the classical circle. In red color is given the classical line. In this case, classical lines is tangent to the classical circle. In other case, we have that in the brown case, we have not this situation. So now we will give some condition for isotangency. Consider an isocircle given in this way and the isoline given in this way. By the previous section, we have that this isocircle and isoline have only one common point if the quantity D is equal to 0. And here are given some examples for isocircles and isolines, which have only one common point. This is the first example. Then the corresponding isolift have no any common points. Here we consider as next example, consider this isocircle given with this way. The isotopic elements are these elements. We will search if there is an isoline given with this equation, so that the isoline and the isocircle have a unique common point. After the direct computations, we get that we have two isolines with this property. As next example, we consider the isotopic element head T to be equal to 3, head T1 to be equal to 5, head T2 to be equal to 10, and the isoline head L to be given with this equation. We will find an isocircle so that the isocircle head C and the isoline head L have a unique common point. After the direct computation, we find that the isocircle has to be this isocircle given with this equation. And now we will investigate isotangent from an isopoint. Now we consider the isocircle given with this equation and an isopoint that is outside of the isocircle head C. Because it is outside of the isocircle, we have the following inequality. In this case, the equation of an isotangent to the isocircle is given with this equation, where the isopoint head P lies on the isocircle head C. We will find the isocoordinates of this isopoint. After we do the direct computations and using the definition for isotangent, we get the following representation for P1 and P2. P1 has the following representation, P2 has the following representation, and from here, from any isopoint outside of a given isocircle, there are two isotangents to the isocircle. As first example, we consider the case when the isotopic element head T is equal to 2, head T1 is equal to 4, head T2 is equal to 9, and the isocircle has the following equation. Then it is shown in this way, the following isochord, head P, head Q. In the next example, is shown the isocircle with this equation, and the isochord head P, head Q, where head P and head Q are the following isopoints. The picture in this case is this one. If the isotopic elements are given with these isonumbers, then the isochord is given in this way. The picture is this one in this case. So now we'll consider the behavior between two isocircles. We'll consider two isocircles given with these two equations, and we'll investigate when these isocircles have one common points, two common points, and they have no any common points. After the direct computations, they are given here in the task, the lectures. We get that in the case when this quantity is positive, then we have two common isopoints. When this quantity is equal to 0, we have only one common point, and when this quantity is negative, we have no any common points. In the case when B1 is equal to B2, we get the following two isopoints, which are common for the for both isocircles. As example, we consider for isotopic element head T to be equal to 2, head T1 to be equal to 3, head T2 to be equal to 4. Consider these two isocircles, and these isocircles have no common isopoints. The picture in this case is given with this picture. As next example, we consider for the isotopic elements to be these isonumbers, for the isocircles to be these isocircles with these equations. And in this case, we have two common isopoints, which are given with these isonumbers. And the picture in this case is this one. And the next case, when the isotopic elements are these isonumbers, isocircles are given with these isoequations. Then in this case, we get exactly one common isopoint. And the picture in this case is this one. Okay, thank you for your attention.
Okay, thank you to you.
Interesting and very strange situation, because it is in some cases it is very close to the classical ellipse, in the other cases to the classical circle, but when we have classical circle, the isotangent and tangent are not common points.
can you imagine any physical interpretation of this, or where this would arise, where it would be something interesting rather than just ellipses and circles and tangent lines that we're looking at? What's the difference? I don't see any difference.
Well, there is one. There are what we use in reality the opposite. In other words, we use we assume physical reality, in which case the shape of a particle is not a circle. The section view at least is an ellipse, and then we look for an isotopy such that so that the image, the isotopic image of that ellipse is a perfect circle in isospace. This is necessary, for instance, if we want to necessary for the axiom of a Lie algebra. See at the isotopic level, Lie algebra can only at the abstract level have to be linear for it, and so you have to reconstruct linearity in isospace. And one way of doing it is precisely doing this inverse map.
So maybe the only interesting thing would be at the microscopic level, like quantum mechanics, rather than anything macroscopic is obviously the usual geometry that we know for circles and ellipses. Maybe at that microscopic level you're talking about, that's where it becomes interesting.
Very, very likely. So the only field that we know at this moment is at the microscopic level as far as particle physics. Biology, no. Biology, there is no limit in that.
But early on, Dr. Cruz mentioned the possible applicability of continuum mechanics, and I also had in my mind idea that somehow that this could be related to fluid dynamics, and I made an example of, say, the airfoil of an airplane wing, and so the notion of streamlines, for example, in fluid dynamics, is a physically sort of relevant concept, I think, and if this notion of isotangent is somehow related to the shape of the airplane wing, does that mean we have some kind of new isofluid dynamics in which tangents, in which flows interact differently with surfaces?
Yes,
in some sense?
Yes, but they have to use the opposite map. In other words, you have to reduce a variationally non-self-adjoint system, which is a physical wing moving in the physical medium. That is not the Hamiltonian system. So you have to turn it into a form as a necessary condition to use the optimal control theory. You have to turn that non-Hamiltonian system into an Hamiltonian one. And the only way, therefore, to have a variational principle and therefore do the optimization. The only way, after working for 30, 40 years on this, the only way that we know to do this is via the Iso-Differential Calculus. You embed the non-potential forces in the notion of differential. This was the part I was supposed to deliver on the origin of the origin of the physical origin.
But this would of course be very radical if you could somehow demonstrate that isomathematics allowed for computations in fluid dynamics. It would have enormous implications for engineering applications, for example.
Yes, fluid dynamics, I do not know, but I'm certain for optimal control theory. I delivered a seminar course when I was teaching in the Cambridge area, and I definitely know that indeed, actually there are papers in which the actual shape and dimension of a wing in a 16th media have been used. So for the first time, because the applicable forces are resistive. And this was my supposed presentation of the Iso-Ion.
But I think that there is many examples of materials that are properties that are not isotropic. Then in all of these materials, I think that in a natural way, we can maybe apply ISO mathematics, but because maybe this can express in a better way the properties. One classical example is when we take a bunch of paper, and then we start bending this, and the way of the papers flew is because the no isotropy of this material, for example. Then I think that we can find many examples of these properties in materials. I think that in plastics and polymers and something like this, we can find many examples of materials that have not isotropy. Then I think that they are good examples of this. But the standard techniques of calculus and solution of differential equations are in general working okay for this kind of materials.
The kind of example that I had in mind in fluid dynamics is, I recall specifically the representation of the airfoil being a kind of a distorted teardrop shape, for example, and that air passing over this shape of the wing produces lift. And one way of calculating this is to introduce a mapping. So I like to have the idea of mapping that you mentioned, Dr. Cruz. Like, so we map this teardrop shape and air flowing over it as if it is a cylinder rotating very quickly, right? So the rotation of the cylinder is an analog of the shape of the wing. Right? And so we can solve the equations for air passing over the rotating cylinder to calculate lift. And so we've mapped the problem of a stationary thing, the wing in this case, to a rotating thing in another case. But when we solve the equations, we can solve one of these equations very easily, and the other one is sort of beyond our tools. And so I wonder about this isotopic mathematics. So can we do such mappings using isomathematics? Can we say, here is a wing, the shape of a wing, and here is a rotating cylinder, and they are representing the same thing at an abstract level, but one is kind of related by an isotopy, right, to the other.
Yes, that's a fantastic problem that you pose. Very interesting. The answer is yes. The sectional shape of a wing can be isotopically mapped into a circle, an isocircle, precisely as described by Dr. Georgiev.
But then this, in a sense, is at least partly an answer to Dr. Sobczyk's question. Then that we can, at least in principle, find physical examples where this geometry, this isogeometry, might be applicable. But
yes, yeah.
But we're still looking. We haven't found them yet, though. That's the thing.
Yes, the problem is that the actual formalists are writing in standard calculus. And then we need to explore how to express in isocalculus, for example, the problem. for example, that the example that you present, Professor Page, is one good example of this, how we can transform the conventional problem to another geometry that solve the problem in an easier way. This is, I think, the problem here with the Iso calculus.
Yeah, maybe it's like Lobachevskian geometry that wasn't applied. People didn't even know it existed. So, okay, maybe we have a totally new geometry, but so far it's not so clear, actually.
From a viewpoint of a calculus, Dr. Cruz, you have another very important point. Whether mathematics can help to simplify a calculation. But this goes back to a question that I raised, but we don't know the answer. Namely, I know that a nonlinear equation, as it is the case for optimal control theory of a true medium, the equation is highly nonlinear. However, I am certain that the isotopic method is isolinear because all the nonlinear terms are embedded into the isotopic element. So the central issue is whether now I know that the solution of an isolinear equation are much easier than much easier than the solution of a general nonlinear equation. The question that we do not know the answer is whether the solution of an isolinear equation, when projected in the original space, provides also one solution of the original nonlinear equation. If the answer is yes, this is a major contribution to the to simplification of calculus. At least there is a solution of nonlinear equation.
Yeah, that's interesting.
And anybody who's interested in working at this problem, I would love to join and write a joint paper. This can be done algebraically, beginning at the algebraic equation, nonlinear turned into an isolinear, and then passing, of course, to all the way to nonlinear in the wave function.
I'm tempted, Dr. Sobczak, to play a little bit on the example that you gave of Lobachevsky space, and I wonder to what extent one could claim that this notion, abstractly at least, is embedded in geometric algebra. I mean that if we allow the notion of, say, vectors in geometric algebra to be paravectors, then we have, in that sense, Minkowski space embedded in G3.
That's right. That's right.
Yes.
And now, that kind of abstract example is a mapping, perhaps, within the geometric algebra language itself, right? So we can map the notion of vectors into paravectors, do some calculation, and then return in some sense. Or maybe I'm extrapolating a little too far. But what I'm suggesting again, I guess, is that geometric algebra is highly relevant here because it's rich enough to contain these concepts within one formal structure. And so when I see the formulas that you write in your draft paper, and I think I can look at this formula as if it's in two different things, or like one, going back to the symbol that you use, the special symbol star for the isotopic element, right? It's when you read it one way, you're reading an expression in geometric algebra, with that special symbol being an element of the geometry. When you read it the other way,
defines the inverse of the iso unit.
Yeah, but when you read that same expression and give slightly different interpretations to exactly the same symbols, then you see that it's an isogeometric algebra. But the expressions are identical, right? That is syntactically the same thing represents two very different things, and the entire thing should be understood in geometrical algebra, but in two different ways. I'm still not quite. So that's why I said earlier when we started that I thought I was kind of optimistic that this would provide a tool to better understand isopity in general as a kind of mapping, as a kind of, but it still isn't clear to me what's being mapped with what, right? In what sense.
Yeah, that's all these calculations we've done here. We see everything has been reduced to usual calculations. It's just with the added structure of this ISO unit and its inverse. Well, actually for each dimension, but actually we can get around that as Dr. Santilli has done with his notations too. So.
But in order to take advantage of this isolinearity, for example, and to actually solve nonlinear equations using some kind of isomathematics, we would have to claim that solving isolinear equations is somehow easier. I mean, I'm not.
No, I think with projective geometry, they've actually done that. In conformal geometry, it reduces problems to projections, and you do get new solutions then to problems.
Mm-hmm.
So there is a possibility of solving differential equations, linear differential equations, and then somehow projecting back from the iso space to get a more general solution than it would seem like.
Okay, well, I think it was a very interesting discussion and presentation today. And Dr. Sobchak, you said you would not be available for the meeting next week.
Yeah,
okay, then my lecture will be next week.
So you would, Dr. Georgiev, you would continue with your lecture.
Yes.
Next week.
Next week.
Yes, and so of course we will record it as usual. And Dr. Sobchak, if you are able and have the time, of course, you'll be able to view the presentation from next week at when the time is convenient to you.
Yes.
Okay.
Okay.
Thank you very much, everyone. I'll see you next week.
Next week. See you.
Have a good trip, Dr. Sobchak.
Thank you very much.
Yeah, the same for you. Yes, a beautiful trip back to Mexico.
Beautiful Mexico. That's right. So thank you.
Bye for now.